Hello and welcome. I'm Pravir, and today's session is exploring new horizons in quantum computation based on a multifaceted view of the double-slit experiment. Now, we all know that quantum computing is an area with massive potential, and this derives from a couple of considerations. First, the promise of exponentially speeding up computing by leveraging quantum mechanical properties, and this is the apparent focus of players in the computing industry, quantum computing industry today. The second derives from the fact that the quantum realm separates the visible from the invisible, and I consider this to be more germane simply because the latter implies that no matter how much we know, there will always be more that we do not know, and this in turn will always be a source of new technologies that will continue to drive us into the future. So this session is going to provide an approach to penetrating the unknown by re-looking at the double-slit experiment and then the possible technologies that will derive from such an exploration. But clearly this will only be the beginnings of such possible technologies, tapping only into the surface, if you will. So this session is going to be structured in the following sections. First, we're going to look at the double-slit experiment. This is going to yield to a consideration of the quantum computational whole. And as we drive further into this, we're going to surface insight from different observers within this double-slit world. And this in itself is going to suggest different quantum computational approaches. And I'll finally summarize and conclude. So looking at the double-slit experiment, I took an extract from a production by PBS Digital Studios. It's called The Quantum Experiment That Broke Reality. So let's listen to what they have to say.
And each bundle can't be broken into smaller parts. So that means that each photon should have to decide whether it's going to go through one slit or the other. It can't split in half and then recombine on the other side. That shouldn't be a problem, as long as you have at least two photons. One photon passes through each slit, and then the two photons interact with each other on the other side and produce our interference path. But here, we get to one of the craziest experimental results in all of physics. The interference pattern is seen even if you fire those photons one at a time. Well, let me back up a bit. The first photon is detected as having arrived at a very particular location on the screen. The second, third, and fourth photons also, they deliver their energy at a single spot, and so they appear to be acting like particles of well-determined position. But check it out. When you keep firing those single photons, you start to see our interference pattern emerge once again. By the way, Veritasium actually conducts this experiment in his excellent series on the double-slit experiment. Really worth a look. This is so bizarre. This pattern has nothing to do with how each photon's energy gets spread out, as was the case with the water wave. Each photon dumps all of its energy at a single point. No, the pattern emerges in the distribution of final positions of many completely unrelated photons. How can that be? Each photon has no idea where previous photons landed or where future photons will land. Yet each photon reaches the screen knowing which regions are the most likely landing spots and which are the least likely. It knows the interference pattern of a pure wave that passed through both slits equally, and it chooses its landing point based on that. It turns out that the photon isn't the only thing that does this.
Okay, so let's step back and look at, or rather consider some thoughts that arise from looking at this double-slit experiment. So, well, first of all, the photons are projected one at a time through two slits, and they create a wave-like interference pattern on a screen behind. So this is quite counterintuitive, because usually if you have a source of light and it's flowing unrestrained through two slits, then you would expect an interference pattern on the back end on a screen. However, the point here is that even when you project a photon one at a time, then it still results in an interference pattern. So some thoughts related to this, or the reasoning as to why this might occur, is the following. It appears that each photon has a knowledge of the interference pattern, as was suggested by the PBS Digital Studio, and knows where to fall on the screen to adhere to that. If this is the case, it's as though the individual photon is crossing limits of time to share knowledge with past and future photons. And in so doing, it's displaying superposition because it's adhering to wave knowledge of many possibilities until it hits the screen. And then there's also an implicit entanglement in this, because all the photons share knowledge with all the other photons in the entire experiment, past and future. And if one thinks about this, this is perhaps consistent with the Copenhagen interpretation. And this is certainly a key interpretation of the double-slit experiment. Now, I want to also offer another interpretation. Of course, the Copenhagen interpretation, or the interpretation that I just went over, I would perhaps term it as a bottom-up or a reductionist interpretation, because it's looking at this experiment from the point of view of each photon. And then we have the perception, or rather the perception arises, that photons are connected to the past and future and assume infinite values until they hit the screen. And so this idea gets reinforced. However, if we also interpret this double-slit experiment from the top down, so if the same experiment is viewed as a totality, then no part can be separated from the whole. And there's a suggestion of a whole, WL, that is wrapped in the space-time configuration encompassing the entire experiment. So let's think about this a little bit more. So if we have a wholeness of light, and this light has a certain set of quantum properties, say L1 through Ln, then we may say that every photon is correlated, every photon that leaves this source, if you will, is correlated to one of the other of these properties, L1 through Ln. And as it finds itself on the final screen behind the double slit, then it adheres to a function that's dependent on the correlation that it had with the property with which it was, in a sense, aligned with from the beginning of this experiment. So if this is the case, then what we're saying is that there's a functional interpretation, meaning that every photon has a functional aspect. And here the function is BL1 through BLN. And the individual photons contribute to the final interference pattern based on this functional basis, as summarized by this graphic. So in this interpretation, there's no need for the photons to be connected across time. There's no need for them to assume infinite values. So there's something other than the Copenhagen interpretation that they then begin to adhere to. And in separate considerations, I derived or suggested another interpretation that I call the quaternary interpretation of quantum dynamics. But let's now go down this path of the top-down experiment, or the top-down interpretation, a little bit more. As we do, pay attention to which interpretation you intuitively align with or adhere to. As we continue to explore this double-slit experiment, I want to introduce you to a cast of characters. We've already been introduced to WL, which can be thought of as a wholeness of light that has a number of quantum properties embedded in it. Now, when we take the bottom-up interpretation of the reductionist point of view, then this creates a function R of WL. And we can then say that if we probe into R of WL, there will be certain R properties that arise. And so these are a couple of actors from the bottom up. If we now consider the second interpretation, as I suggested, there's a number of L properties that this WL has implicit in it. And what we saw on this screen behind was then another actor called BL, which was related to these L properties. And I'm going to introduce another actor, SL, which is a seeded layer, and we'll get to this in a few minutes. And then EL, which is an evolutionary layer. And then this branch suggests a wholeness of a different kind than RWL, because there's a buildup of whatever is in WL progressively. So there's something that we're calling UWL, and this can further be the foundation for creating something called VWL. And then I want to introduce you to another actor, just as we have a source of light that has some set of functionality embedded in it. Here, consider another source of light with another set of functionality. And then there's a combination of these that creates a unique world, if you will. So these are some actors that we're going to probe into in more detail in these subsequent slides. The point of this is that if we look at these different branches, what we have is 4 different possibilities in terms of thinking about quantum computation. And I want to suggest that this possibility here, where we reduce the quantum objects, or rather looked at quantum objects that were outputs from WL, and in the act of measurement, we reduce them. And so this is one branch that we can certainly go down, but there's other branches that also are being suggested here. So let's think about this current quantum computational approach a little bit more. So I would make the case that this current quantum computational approach is a function of decomposition and recomposition. So what do I mean? So we took a whole source of light, and then as quantum objects are projected, we measure these quantum objects, which are photons. In the act of measurement of the quantum object, we've now reduced this whole into something that's measurable. And then we use probability and statistics to recompose what we had measured into a probability-based wave-like function. This probability-based wave-like function, I want to make the case, is different than what we see as a double-slit interference pattern. It may appear to have the same behaviors mathematically, but in fact, it is not the same thing as the interference pattern that we see on the back end, and it's not the same thing as what's possible with WL, as I'll get into in a few minutes. I also want to make the case that the manufactured qubit is, if we think about it, a function of RWL and the R property. So it's not, a manufactured qubit is not dealing with the quantum properties that are implicit in WL, but it's dealing with measured quantum objects that now have a different set of properties, and there's a different substrate of computation that's built on this, what I call the R substrate, if you will. An analogy that I want to draw attention to is, suppose we consider the realm of space and time. There's a limit to how accurately we can perceive and measure space and time, and it's been hypothesized by some that it would require an infinite amount of energy to penetrate into the smallest quantum of space and time, space or time. And it's simply because space and time are emergent properties, it's not possible to penetrate beyond a certain granularity. So if we do try to penetrate, though, this would in turn cause a collapse into a local black hole, and all the laws of physics would break down according to this thought experiment. I want to suggest that some of the difficulties that we see in standard quantum computation may be of a similar nature. Already we have things like decoherence and lack of stability, lack of ability to propagate quantum states, lack of scalability. And I want to suggest that no matter how much energy we put into it, we're not going to get any better at this. And if we put an exorbitant amount of energy, it also would collapse into a local black hole and break down all laws of physics. And this perhaps is a clue that there might be other approaches to consider how nature at the quantum level operates. And that's what's being suggested by these other branches here that we're going to get into in a minute. But just summarizing the branch that we went over, there's a quantum computational whole that's represented by WL. In decomposing and recomposing WL, the focus is now on RWL. And this RWL is not the same thing as WL. So there are other parts beyond RWL that should also be possible that get to morph the wholeness here. So with that, let's now consider a quantum computational whole. So I'm going to start with a thought experiment to construct a world that's based on the whole. So in this world, each photon that originates in the quantum computational whole in WL is in reality bringing forth or carrying something of WL. So let's just imagine that to be the case. Now, WL can be thought of as having unique and distinct quantum properties that I went over, and that's represented by the set L1 through Ln. Each photon then can be thought of as being related to or derived from one of the elements. Every photon that leaves this is correlated to one of Ln, L1 through Ln. And when it hits the screen behind the double slit, it takes on the form of BL. So here we have functions of L1 through Ln, and that function is BL of the form BL, where L is related to one of the elements that derive from WL. So each photon is now adhering to a certain function that is itself created from WL as a whole. In this thought experiment, each of the strands highlights a unique aspect of WL. And physically, of course, the fact that you've got photons that show up in each of these different strands means that there's a lot of functionality embedded in WL. This strand will practically consist of up to infinite photons that each highlight some subtle variation or nuance related to the set it belongs to. So as we consider any of these strands here, then we can imagine that BL1 has infinite number of nuanced photons. So there are different elements that define this set, and each element is completely unique. Imagine now that the layer consisting of BL is the base layer. So we're talking about a double slit world. So this is the base layer. It manifests something of WL, but WL is an unseizable whole and has a lot more to it. So BL is not able to bring out everything that WL is. WL wants to push forward more of what it is. And so through a process of combination, there are seeds that are created that leverage the material forms of BL. So I suggested that each of these sets, BL1 through BLN, has infinite elements. Now we can think of a second layer, SL, that basically has unique seeds that each seed is different combinations of unique combinations of elements from each of these different sets. And so we have the basis of a second layer, and mathematically we can depict it in such a manner. And this then brings out something different. We become aware of something else that is surfacing from this whole that WL is. So this process continues with many layers surfacing, each capturing more of WL, but never the entirety of what WL is. And in this way, form and property can combine to create a world built from the quantum whole. So we have EL then that can be thought of as a continuing form or an evolving form that now is based on SL and the subsequent layers that are derived from this. Now, before I continue, I want to just have us look at the real world for a moment here. And I'm going to take us through something I call reverse extrapolation and then forward extrapolation to create a world that is similar to the world that I just went over, the hypothetical world that's derived from some quantum computational whole that light is. And let's just consider something that's very granular. Let's consider a living cell. So we have a living cell that has, it's known that any living cell has four molecular plans, whether it's a plant cell, animal cell, or human cell. And when we look at these four molecular plans, they're called proteins, polysaccharides, nucleic acids, and lipids. Now, if we actually ask ourselves, what's the essence of these different molecular plans? I can make the case that, okay, let's think about lipids, for instance. Lipids create natural compartments in cells, and this allows work specialization and harmony to arise. So I could say that lipid, when you really reduce it to its core functionality, it has something to do with harmony. Now, nucleic acids, we know, create the DNA of cells. DNA creates the libraries create the information or store the information by which all the components in the cells can act, and by which the knowledge of one generation of cells is given to another generation of cells. So I can make the case that nucleic acids, when we really think about it, is exercising a functionality of knowledge. Now, polysaccharides, we know, are chains of sugar, and here these provide energy to the cell. So I can say that in its core, it's exercising a functionality of power. And proteins, we know, for example, that there are over 30,000 different proteins in a human cell. They're involved in all kinds of activities. They make the work possible in the cell. They're present throughout the cell. They provide service. So I can reduce this to some functionality that I'm calling presence. So in essence, I'm saying that what's being represented here, these molecular plans, is a fourfold functionality that I'm calling presence, power, knowledge, harmony. Now, if I go back and reverse extrapolate and go to a lower level of granularity, so here we're looking at the periodic table, and there's a classification into S shell, D shell, P shell, and F shell. And here I can make the case, for example, that if we consider S shell atoms, for instance, so let's just consider hydrogen and helium to be surrogates of the S shell atom. And we know that they are involved in processes of nuclear fusion. So there's a lot of power and energy related to them. And so I can make the case that it has something to do with this functionality of power. When I look at D shell atoms, this creates the vast infrastructure all around us. We have elements like iron, nickel, cobalt, aluminum, copper, and so on. And so I can make the case that this has something to do with this functionality. It's a carrier of something of presence. When we look at F shell atoms, I can make the case that this is an experiment in collectivity at the atomic level, because you have atoms of the largest atomic number. And so it's a carrier of something that we call harmony. And when I look at P shell atoms, we got things like elements like carbon and silicon that are the basis of computing life, both inanimate and animate. And then there's different archetypes that exist within the p-shell elements that represent, in a sense, elements across the periodic table. So I could make the case that these archetypes all are expressing the core knowledge that exists across the periodic table. So it's a carrier of knowledge. Now, if you go down a level to the standard model or the level of quantum particles, we know that the standard model has 4 different kinds of quantum particles. There's the Higgs boson, leptons, quarks, and bosons. If I think about bosons, then I know that any quantum particle relates to another or combines with another due to bosons. So bosons has something to do with harmony. I know that, for example, quarks are the components of any protons, and protons determine the atomic number. Atomic number determines the behavior of an element. So I can say that quarks are a carrier of knowledge. If we think about a surrogate of lepton, electron, we know that the release or capture of any electron is accompanied by vast amounts of power. And so I can make the case that the lepton is a carrier of power. And then I know that any quantum particle that has mass has to interact with the Higgs field via the Higgs boson. And so the Higgs boson then becomes a carrier of this thing that we call presence. The point here is that as we look at manifest life in the layers of matter and life, then what becomes evident is a simple pattern, a functional pattern, presence, power, knowledge, harmony. And as we then extrapolate, so suppose we had started with this presence, power, knowledge, harmony, then we can see that with any subsequent layer of matter or life that emerges, more of what's contained in this quantum whole is coming forward. So presence, power, knowledge, harmony have a smaller meaning here as compared with here. So for example, at the level of cells, as I suggested, there's 30,000 different proteins. So the functionality of what presence stands for has become much more sophisticated. So more of what is contained in the quantum computational whole is being brought out. And this, just to give us a reminder, we're talking about the same thing here. We're talking about constructing a world based on the quantum computational whole. So here we've taken an example of it. But the point being is that if we assume that this is a possibility, then there's a different quantum computational architecture that's required to leverage it. So the only way to begin to make sense of this quantum computational whole is to first realize, imagine that it exists. And I tried to give an example of that with the manifest layers of matter and life that are all expressions of some kind of quantum computational whole that exists at the quantum levels. Now, the point is that we would need to use instrumentation based on BL, SL, or EL, where E is some evolving functional form in the possibly endless journey that continues to express something more of WL. And this instrumentation implies a different quantum computational architecture that's honed in on perceiving quantum properties and their dynamics through logic, mathematics, and gate structure based on EL. And later on in this presentation, I'll spend a couple of minutes on this. Now, let's begin to add insight from different observers in the double-slit world. So observer 1, I'd make the case, is our current quantum computational focus. And we start here by considering the act of employing probability and statistics to decompose and recompose WLs. That becomes, in a sense, our act of observation. Observer 1 is all about measuring a quantum object and then employing probability and statistics to therefore decompose and recompose WL. So this act of observation results in RWL down this branch that is fundamentally different from the wholeness of WL. So WL still exists as a whole, except we're not dealing with that anymore. We may think we're dealing with WL, but in reality, we are now dealing with something that is RWL. So if WL contained L properties, L1 through Ln, then we can think of RWL as containing a different set of observed properties, R1 through Rm. And we can think of R element of this set as being superposed with all other elements of the R set. So when we're doing superposition, we're actually superposing this R set. And then we can think of similarly entangled R elements will result in a new state that we're calling the entanglement of R1 through Rm. So the quantum computing possibilities of RWL will be based on the R set. So it's a different stratum that we're actually building our quantum computing architecture and dynamics on. And this is distinct. It's different from the wholeness that WL represents. So we can do things like superposition, we can do things like entanglement, but we're actually creating a strata just as we have when we compute with digital bits. We've created a strata that then has a binary operation. So here we're creating a strata in which we hope to have qubit type operations where we can leverage things like superposition and entanglement to create the processing possibilities that have been envisioned for quantum computers. However, in this strata, the possibilities of an EL will simply never occur because we're not dealing with wholeness anymore. We're dealing with something different. Now, when I want to delve into the idea of RSET a little bit more. So in today's rendering of quantum computation, we know that qubits that are the equivalent of digital bits can be based on a variety of quantum objects, ions, electrons, photons, that display quantum mechanical properties such as superposition and entanglement. And the whole bet is to be able to build a certain strata with these kind of quantum objects, these qubits, and then leverage the properties of superposition and entanglement in particular ways. And the way we're doing that, there's a couple of approaches. So approach one is to group together a threshold number of qubits, learn to map a real world problem to them, learn to leverage superposition and entanglement to process the possibilities, and then hopefully solve a variety of traditionally intractable computational problems as a result. Now, approach two would be such that qubits can be made to represent atoms and molecules. So this perhaps gets closer to the idea that Richard Feynman had, or perhaps even atoms and molecules can be harnessed to operate as qubits within a controllable gate-based quantum computational environment. Then we can quantum mechanically see new possibilities from the bottom up. And while in themselves, these are great possibilities that absolutely need to be further developed, in focusing on the mechanics of manufactured quantum objects, the quantum hole that keeps silver operating as silver or the integrity of particular protein intact escapes us in this approach. And that represents a different quantum computational possibility. So now we move to observer two, where we might be focusing as a result of our observation either on the R property, which is similar to observer one, or on the L property, which gets to the kind of wholeness that we want. So let's just think of this kind of observation that's happening when we place a measuring device close to the double slit. And depending on how it is measured, it may result in an R property or an L property. If we focus on R properties, then subsequent entanglement, superposition, quantum computational possibilities become similar to what we already discussed in the observer one scenario. And if, however, it's the L property, then depending on how L properties are made to interrelate with other potential L properties, we may again reduce to RWL, or we might change to some other fraction of WL, which is UWL or VWL, which has implicitly the wholeness that we're after, that we haven't been able to leverage with the RWL approach. Now, when we consider observer three, and this will increase the L property function focus. So in the observer 2 scenario, we can bifurcate into either possibility, but with the observer 3 scenario, we're going to remain securely on the L property branches here. And let's think about this metaphorically as represented by the screen that we know by definition has these different strands that are each built on, in our thought experiment, on the L properties of WL. So the resulting quantum computational possibilities would then be a variation on that defined observer 2. And if we reinforce this UWL, since it's based on the functionality of L1 through Ln, it could become a larger set. And this is where we get introduced to the second actor in this stream, which is VWL, which would bring out more of the wholeness of WL. Now, we can think about observer 4 as being the intersection of holes. So we now bring another hole that has a different intent. And this is the fourth kind of observation that can take place within this double-slit world. And the way to think about this intent is that it could be thought-based or it could be emotion-based. And the intersection of WL and WOLO will result in another unique hole that's basically W plus WO, L plus LO. And so it's a merger of sorts. And we would have two such intent-based observers interacting with the same WL, could therefore cause different quantum computational outcomes, with the observers experiencing different objective realities. And there appears to be some experimentation to this effect that had been documented in the MIT Technology Review from a few years ago. Let's just summarize the key ideas that we went through with the observers. So in the point of view elaborated here, the quantum level is interpreted as a complex, sensitive, adjustable via feedback. And as such, there are different ways to conduct quantum computation that will require different architectures that result in completely different outcomes. The default industry approach, I want to make the case, seems to be captured by observer 1. However, in contrast, you got observers 2, 3, and 4 that represent unique and different types of quantum computing opportunities that progressively reach into more and more creative realms based on the evolving form EL as it journeys to quantum wholeness as represented by WL. Think of the layers of matter in life, each expressing more of the sophistication of what's embedded in that simple fourfold pattern of knowledge, power, presence, harmony that shows itself as more and more intricate forms of what that is represented by that wholeness. So now let's consider different quantum computational approaches. So basically taking these observers and just drawing the connection to different architectures that are suggested by them. So if we take the existing quantum computation approach, then this is the observer 1 scenario. And just to recap, it's the commonly accepted quantum computing species in which measured quantum objects are then subject to statistics and probability. So it's about measuring the quantum objects and then using statistics and probability. And these quantum objects would also allow entanglement, superposition, and computational speed up. And that's really the core principles of what's driving the architecture of quantum computing today. However, I want to suggest a different kind of quantum computer. I'd call it a function-based quantum computer. And basically, this starts with the observer 2 scenario, where we're measuring differently than the way measurement is happening in the observer 1 scenario. So the measurement itself may allow something of the computational whole to be measured rather than the reduced quantum object. And measuring the whole, though, requires requires a different measurement paradigm than the one in practice now. And gates would also need to propagate property or function derived from the quantum computational whole. So gates would have a different purpose in this architecture, and there would be a different mathematics that would drive it. It's not based on probability and statistics, as in the scenario one, but it's based on function. And there would be this unique function-based mathematics that allows the manipulation of function that we had begun to get a sense of exists when we're looking at this. And I just want to also say that I've in fact filed a non-provisional patent where I've defined a number of different gates that could be used to measure quantum phenomena differently. And I've also begun to lay out the beginnings of the mathematics that would drive such a functional quantum computer. So now getting to a third possibility, we have the observer 3 scenario that's based on perceiving more of the wholeness. So, and more of the wholeness, we're using the strands of the interference pattern on the screen as the metaphor here. And this would also be built on a function-based computer, meaning that we'd have different gates and different mathematics that I just gave you a glimpse of. And so the computer looks at the quantum level differently, and different combinations of gates can be combined to create higher levels of computing sophistication. And the arbitration of the higher level of wholeness that has implicit in it a large range of functions becomes then the basis of a more sophisticated quantum computing possibility. And this also would require a reinterpretation of the notion of quanta, and also reinterpretations of fundamental quantum computational anchors that have been established by Feynman, Euler, Schrödinger, Heisenberg. And I've done some beginning work in this area. I've got IEEE articles in all these areas to take a crack at how these might be different, or how we could reinterpret these formulas and Euler's identity differently, and so on. So now we have wholenesses interacting, which is the observer 4 scenario, where you got two wholenesses made to interact. And this also would require some kind of function-based quantum computer. But in this scenario, you've also got human beings who become part of the quantum computational architecture. And here I have also done a little bit of work, and I haven't checked who else has done work in this area, but I've written again a few IEEE papers, a nanocyborg paper, and also a paper that looks at quantum computation and the universe as a complex adaptive system. So to summarize, right, to get the essence of this range of actors, I want to suggest that if we think about WL, in some sense, she's like a hidden empress. And if we think about RWL, which is what we are dealing with our current quantum computation approaches, it's like a utilitarian administrator. If we think about R properties, these are administrative factors. If we think about L properties, these are ideas and virtues. If we think about BL, then here we have the quintessential idealist. And then SL is the architect that it takes ideals and tries to create something whole. And you have EL, that's a warrior that's continually breaking through new ground. You have UWL, that's a magician, because you begin to see the first different kind of wholeness that comes forward. VWL is the artistic scientist, because now you've moved beyond the realm of magic, what appeared to be magic, and you're using a very artistic approach to science. And when you think about Volo, then this can be thought of as an emperor. And the combination of bringing these together, the empress and the emperor, basically is empire building. So entirely new possibilities of wholeness that we then are computing with. So there's a roadmap. I want to suggest that there's a couple of different roadmaps here. There's the existing roadmap, which is based on RWL and art properties. But then when we consider the other actors, I would say that there's three different roadmaps that each have as a prerequisite the previous one. So you've got this function-based quantum computer that essentially in its first stages can be used to measure things differently. And so this is built on BL and L properties. Then you've got a more sophisticated function-based quantum computer that you're dealing with SLEL, UWL, VWL, and then you've got wholenesses interacting that's dealing with WOLO, WL, and the combination. And each of these mini roadmaps requires the previous one to be completed. But the important point here is that while we are estimating that it'll take 10 years for the RWL, R property kind of quantum computers to create some really extraordinary functionality and applications that can be scalable. If we were to begin development with these other possibilities, I would suggest that within 10 years, we would have something similar. And because we're just dealing with an orthogonal set of possibilities here. Key takeaways: the double-slit experiment can function as a simple framework to make an exploration into the quantum unknown. And that's its extraordinary utility here. There are unconsidered potential technologies that will surface from such an exploration. And finally, there's a dual track quantum computing roadmap leading from the near to the far. Thank you.